Hey everyone, so today I thought I would showcase how productive one can be using the LLVM bindings from OCaml in order to write a compiler. And to do that, I'm going to be writing a very simple compiler today for a very simple arithmetic language. So as you can see here, I've got Emacs open with a sort of base project set up, and that's all compiling and running just fine, as you can see. So if we look at the files real quick, you can see that I've simply got a June project that's using this main module that I've written here, and it's going to be using the LLVM libraries. I'm not going to cover OPAM or setting up packages or stuff like that, or even June in this tutorial. I'm kind of assuming that as background, and even then, it's not too difficult to get up and running with. And for simplicity in this June project, I've sort of downgraded the language version such that I can just have it all in this single directory for simplicity. All right, so let's jump into the kind of language that we're going to be compiling. So I've got this demo LL file here, which is like an LLVM IR source file, where we can write LLVM IR just to demonstrate the lowering that I'm intending to produce using the bindings. So as you can see, it's a very simple language. It's effectively an arithmetic language, where variables are going to be bound by these sort of function definitions here, and these will map very straightforward onto the LLVM IR, which I hope to demonstrate. And just to demonstrate it right now, I'm going to assume some familiarity with LLVM IR, but it's really not necessary. I think that we're going to be using a sort of subset of the overall concepts in static single assignment, or even just in instruction wise in the LLVM stuff. So let's just see how that would lower. So as this is a function, we're going to define a function with a certain return type, and this will be a 32-bit integer with a certain name. So we use this symbol here to denote that it's a sort of global name. And then we'll list off the arguments, which again are going to be 32-bit integers. So sorry, I can't type that. So let's just list them off. Using percent signs for these names here. If anyone's copying along, be sure not to name these as integers, because LLVM has its own sort of internal tracking, which could go wrong for you. Alright, so here we are. And so if anyone watching has ever written an evaluator, you'll know that there's a kind of process by which this is done in a certain order, right? It's linearized out. This is kind of expressing compound semantics. So we could have any kind of thing here, like arbitrarily nested sub-expressions. But at the end of the day, you need to kind of evaluate it bottom up. And so in this, due to sort of conventions around the sort of precedence of this, we're going to evaluate x times y, i.e. these two parameters multiplied together. And then we're going to add this z variable on. So in order to do that, we just use simple instructions in LLVM. There's one for multiplication, there's one for addition, there's one for returning. And that's kind of the only ones that I'm actually going to be using today, really. So let's introduce some new, another sort of binding here. It's not really a binding, but I won't get into that. So let's multiply x and y together. So I'm just going to use the mul instruction, and each of the operands are going to be I32, as is the result. So in LLVM, the result of an arithmetic instruction must match its operands. So we can just simply list out x, and we can just simply list out y. So there's the multiplication. Let's just call another variable b, and we'll add a to z, like that. So this is this sort of part. But of course, since the result of this is going to be the result of evaluating this function, we also need to return the value. So we'll just use the ret instruction here and cite that binding that we created here, referring to this instruction. All right, so that's fine. That should all work just well. Make sure, yep, looks good. So if we run this, if we run the LLVM compiler over this, as you can see, we actually get out assembly for the current target that I'm on, which is 64-bit x86. And as you can see, it's kind of been quite clever with the instruction selection it's done. But yeah, so the idea of this video will be to show how quick and easy it is to sort of in OCaml represent this program, as a sort of abstract syntax tree, but then also write something that uses the bindings, which may be overkill, and I'll make another video in the future about how you could avoid using the bindings and do this linearization yourself, because it's a very straightforward algorithm. Alright, so let's jump back into our OCaml file, and we'll get rid of this. So the first thing we need to do is have a representation of this. So let's just start by defining expressions. So we'll have one for sort of binary operations, and we'll have one for variables. And I haven't shown it here, but we'll also have one for things like integer literals. So get back to the OCaml file. For organizational purposes, I'm going to use submodules, but it's not really the done thing, I don't think, to sort of put it all in one file. But for this video, I think it should be just fine. Let's get rid of this in the meantime. So let's create a module called expression. And inside of here, we're going to have type t, which is just going to be, the sort of convention is that something represented by a module or related to the module will be called t, for the type. So we're going to have integers that are going to carry ints. We're going to have variables, which just sort of are going to be named, and we'll use a string to name them. And then we need to have a concept of a binary operation being applied. So let's call it BOP, but now we need an operator, so let's quickly factor out another type called BOP, and that will support addition, subtraction, and multiplication. So BOP of BOP, and then we need, for each subtree, we're going to have a left and right subtree, because we have two operands to our instructions, as you can see here. So just a simple abstract syntax tree, nothing too crazy. So BOP by T, and for fun, let's add another thing. We'll say call of string by T list, right? So we're going to be able to call a function. So from the syntax here, that kind of should have been clear that we're going to have calls as well, but I didn't mention that before. But of course, it's more just a kind of factoring out of sub-expressions more so than anything kind of useful. Like, I don't think we're going to be able to do recursion with this without a sort of conditional construct telling us when to stop. So it's really just to show the extent of how easy it is to emit different constructs in LVM. Right. So now that we've got that, that's the kind of right-hand side of this, right? That represents the expressions, but now we need a way to sort of bind the variables, right? So we need a sort of function abstraction. So let's create another type for that inside of our ML file. And let's just call this type, I don't know, def, and we'll say it's a function of a string, so that's the name, a bunch of arguments, so a string list, and then the body, right, which is an expression, right, so T. And that's enough. This is, if you're writing a real compiler that has to parse this, you'd probably factor this out into its own file and its own different function and stuff like that. But for this, as I said before, we'll just keep it in one file. All right, so now, following this kind of organizational structure, let's create another module just for fun, call it compiler, right? And as I mentioned earlier in my June file, I'm already linking against LLVM, so if I kind of show you this, I can already see everything here. I've not used these bindings in a little while, but hopefully I remember enough of it to be productive here. So as you can see, it's very straightforward. We've got LL values, which actually effectively are representations of actual LLVM values from the C++ API. All right. So we've opened LLVM just to kind of stop me having to write LLVM dot to access it, right? So it kind of brings everything into scope for us. And in a similar fashion, we'll just do the same for expression to keep it simple. And now, to give some LLVM background, this file here is effectively defining an LLVM module. And the modules are basically things that contain global values, such as sort of hard-coded data, such as strings that that have been relocated, in such like in a C program where you have a string literal. So that kind of would be declared up here, defined up here somewhere. And so, the modules will contain that kind of stuff along with functions, and functions themselves contain basic blocks. They're kind of implicit here as I haven't named a block, but there is a basic block here that contains all of these instructions. So we have to sort of make that clear in the bindings. So let's quickly create a context. So we'll say let ctx equal create context. And this is just a function that's going to give us an LVM context, as you can see down here. We give it unit and we get back a context. So you can have basically a single context with multiple modules that are sort of owned by it in a sense. But I don't think the modules can outlive the context. But if someone knows more than that, then feel free to comment in a correction. So now we also need a module as well. That will be the result of, or it's going to be where we're going to be putting our our list of functions that we're going to be compiling. So let's just call it MD. So that's going to be create a module. It needs the context. Then we'll give it a name. Let's just call it arithmetic. Whoops, arithmetic. And then we also need some types, but I don't want to get too into that. So let's just say that I32 requires the context, right? So this is something that takes the context and gives us the specific 32-bit integer type for that context. And yeah, that should be enough for now. Okay, so let's go about writing how you would define a compiler that just compiles, singular functions, and then we'll get onto the part that actually compiles the expression part of the function. So we'll say compile def. So let compile def, and because we don't have multiple cases, it's a sort of singular constructor. We'll just sort of pattern match on it here. So you have f, a bunch of x's that sort of binds variables over some expression e. So the first thing we need to do, of course, is actually define it in the module. So we have to create the function. So if we look at the bindings, there should be a function called define function. And this takes the name and then a type and then the module that it's going to be defined in, and it results in giving us back an LVM value that represents that function, right? So we can then use that in some place or ignore it. So let's do that. But as you can see, we need the type. And so to express that in LVM, we'll use another function called function type. And if we quickly look at what that requires, it requires the return type along with an array with all of the argument types as well. And then it will just give us a function type, represented by this. So since it's kind of monotypical in a sense, i.e. all of these values are just going to be, whatever As a fun note, LLVM actually supports arbitrary width integers, so you could actually make this, whatever you want, right? And it would still compile it just fine, albeit what you get at the end might not be what you expect. So yeah, I'm just going 32 inches, as I say, for simplicity. It's a very common size for it to be. All right, so we basically need to give this an array that contains, if the length this is n, it needs to have n of these in effect, so n I32 types. So let's do that, right? So let's just say very quickly that the function type is going to be function type, and its return type is of course this. And then to create the array, just very messy, we use array.init, which expects a sort of number, and then a function which maps each of the indices up to this number to a value. So I can do array.init, and I can source the length of this list, i.e. the number of parameters, and then just kind of give it a const function that returns I32 each time, regardless of its argument. And that should be enough. So you can see here we've got the type. And then we can create the sort of functional value by doing define function. And as I said before, we give it the name, and then the type, and then the module that it's defined in. And that should be enough to define that, as you can see. So that's enough, right? So we've now got a function that's now defined in the module, and define as opposed to the function declare. So there's another function called declare, but what that does is it sort of just makes it available for use, such that it's almost like a prototype, such as in C. It kind of makes it kind of defines the signature such that we can call it. But it could exist in a different translation unit. It could be linked somewhere else later on. But define actually creates a function and creates an entry block for us, and so that's very useful. Otherwise, we need to do that manually. So now that we've done that, it becomes clear that we need a means by which, during compilation of expressions, to actually find variables and what they refer to. So we've informed the function that it's going to have a certain number of arguments with this monotype here, this single type. So we need to have a sort of context or an environment. So to do that, I'm going to create a functional map here. So let's just say a string map is equal to map.make. So we're applying this functor here with string, and now we've got effectively a persistent map that we can use to map strings to values. So then what we need to do is effectively fetch out each one of the parameters that LLVM will have defined for us. So if we were to declare this, then we would have a bunch of parameters that we can fetch via index, or we can get an array of them, whatever, from the bindings. So let's go ahead and just create an environment. So the environment, I'm going to do it quite messily. I'm just going to fold this list with an index, I think. So it's going to be, the general pattern will be that I fold left to kind of take these in order. And of course, this is expecting something, this is kind of out of date. They renamed this, but it doesn't matter. The accumulator B, and then it turns the accumulator, and it starts the accumulator, then a list of B's, and we'll get back this sort of accumulated value. And the accumulated value is going to be the environment. But because I want to carry the index in order to fetch it, which wouldn't happen unless I zip this with a sort of list containing all the indices, I'm going to carry that as well. So I'm going to have some function here, and then the thing we're folding over, of course. So the thing I'm folding over is going to have 0, then sm.empty, i.e. an empty map, and then it's going to take x's. And inside of here, of course, we're going to have the thing we're folding over, which is going to have an index and also the environment, and then also the variable x. And this is the name of the variable, of course. So in order to create this binding, what we're going to do is we're going to say i+1 in order to sort of advance it for the next time that this is called. And then we're going to add into the environment. So we're going to add key value and the environment, so x. And how do we get the value out? We're going to call param, which is a function which takes a function value and an index and will give you the parameter, corresponding to that index. So we're going to be giving it the function value as we defined before, along with the current index. And that should be enough to add it into here. But of course, this will be returning a tuple, so we're going to have to project out the actual map that we want, i.e. the environment. So let's just messily say second, right? We'll project it out. The second component of this tuple is what we want. Now you can see it has the correct type. So that's kind of all we need so far. So now we need to define a way to actually evaluate an expression, an expression up here given a bunch of bindings. So let's create another function that we'll just call compile expr. This takes an environment, and it's going to be a function that pattern matches over all of the constructors here. So in the case of just an integer literal, we'll use a function called constant from the LLVM bindings, which expects a type and then also the value, and it will give us an LLVM value sort of that represents that integer. So I32 as before, and then I, so that's fine. And then in the case of a variable, we're just going to look it up. So I'm not doing a bunch of semantic checks here, to be clear. So there's a lot of things that you could do to sort of break this from a user standpoint. Like you could define a function which has clashing names, like you know, all the names of the parameters aren't unique, or you could define a function that's already in scope or something like that. Lots of semantic issues I'm kind of, you know, skirting over in this video to keep it very small and simple. But those are all easy to do as an exercise. So we'll call find on this, and we don't really care whether or not we find it. So we'll just search for x in the environment, and now as you can see, it will tell us that we haven't matched and everything. So what we've got to do, we've got to work out how to do binary operations and calls. So that's straightforward as well. So for the binary operation case, we've got the operator, we've got the left-hand subtree and the right-hand subtree. And if you've ever written an evaluator, you'll know that you sort of have to do something recursively here. And so the type of this function, as it's been inferred, is that it takes a sort of environment, takes an expression, and will give us an LLVM value back. So we can call that recursively. So let's just shadow it, which isn't the best practice, but it should be fine for us. So we'll just sort of shadow L and say compile expr with this environment, you know, the left-hand subtree, and the same thing we'll do for R as well. So the right-hand subtree, and then we need to be able to build the actual corresponding operation, the actual corresponding instruction for the arithmetic operation. So to do that, I'm going to create another function really quickly, and we'll call it op of op, you know, following a sort of weird naming convention used in OCaml. And what this will do is it's going to map between this type we defined up here of these null constructors representing operations to the actual thing that builds it. And this is the kind of first time that we're going to build an instruction. And so to do that, we need to use what we'd call an IR builder from the LLVM API. So let's go up here and just call it B. And I think you just call it builder. Yeah, builder, and you give it the context. And then we'll come back down to here. So when you have a builder, you have to position it in a certain place in a basic block in order to actually emit an instruction there. So that's what I was sort of saying earlier about a sort of implicit linearization happening when we're using this API. So we'll get down here and we'll call a function called position at end, which is just going to put it at the end of a block. So we need to tell it which block, and then tell which builder we're positioning. So the block is going to be the entry block. So conveniently, there's a function that does that. So it takes the function value and will give us back the entry block of that function, and then we'll give it the builder. So that's one step closer to emitting something. So now, again, we'll come back here and we'll map these to actual functions. So build add, and as you'll see a sort of pattern emerging here, where we have, you know, build sub as well, build mul as well, build mul. And if we look at the type of this, it basically takes two values and then allows us to give some sort of metadata as a name, and then you know, asks us what builder we're going to be using to build it. So down here, and sorry, I need to mark this as recursive, of course. So down here, we will now just say op of op, and we'll give it the op, and we'll give it these evaluated subtrees, i.e. these LLVM values. So L and R, and I don't really care, I'm going to ask LLVM to sort of create a name for us, or have no name, such that when we print it, it's going to sort of deterministically generate a name for us using a slot tracking mechanism that's built into LLVM. So that should be good. Okay, we also need to give it the builder. All right, and of course this is returning an LLVM value, so this is all we need to do in this case. So now we only have one missing case, which is the case of calls. So let's do that. So let's say we're calling f with a bunch of expressions. So of course we know that we need to evaluate these, so that's kind of straightforward. We can just map over them. So let's, again, we'll shadow, maybe not the best practice. So we'll map over it with compile expr, same environment. You know, the environment's not changing. You know, the environment's kind of fixed in a sense, right? You know, you could add language constructs that allow you to shadow the environment in some way, i.e., you know, a sort of user-defined construct, like, you know, in certain languages, even in OCaml, like we've done here, we could shadow, and we could do that sort of dynamically. Like we could be emitting code that's changing this map, but for our cases, we only have one way to introduce bindings, which is going to be via parameterization. So we never change this environment. So yeah, we're going to map over these e's to evaluate them. So now we're going to have a list of LLVM values. And then it just comes down to sort of finding this function. So we're going to call a function called lookup function from the LLVM bindings. And this takes the name and the module, and then it gives us an option saying, you know, whether or not we have it. So the name is f in this module. So let's say we have some f, again we're shadowing, and let's say if we don't have it, i.e. the none case, we'll just fail, right, with no message, because we're very helpful. So yeah, this is a function value, so we can just now build a call. So let's say build call, and this expects the thing that we're calling, so the function that we're calling, along with an array of evaluated values, and then obviously, like before, a name that we could give it, some sort of metadata, and the builder. So we're going to be calling this f, and now we need to just have an array rather annoyingly. So what we'll do is we'll do array of list, and we'll give it ease, and then was it the name, and then the builder. Yep, looks good. So now we've defined everything that we need in order to sort of emit the instructions. And we've, of course, like before, we've created the environment, so we've been able to map these names to actual LLVM parameter values, and then we've started by putting the builder that we've made at the end, at the end of the entry block, such that we can start emitting code there. So then all that remains to do is basically evaluate it to a value, so a sort of final return value. So let's just say rv equals, and then we'll call compile expr with the environment that we folded to get, and then the body of the function e, and then we will have to return it, right? So we haven't got anything here that returns it, because that's a kind of top level construct that relies on actually evaluating the body of the function. So we'll put in the code to return it here. So in order to do that, we'll just say build rep, and it just expects a value in the builder. So that's convenient. We'll just give it rv and b, and that's enough. But now it's returning a value which we don't actually need, so we can just ignore that. So we'll call ignore, and now of course it just returns unit, right, which is what we want. And so in order to compile a list of functions, what we'll do is we'll just say compile defs. I have a bunch of f's. We'll just say list.iter compile def f's, and then we'll return the module, right, to keep it very simple. And that should be us. So in 55 lines, I believe we've managed to create the compiler. So now it just comes down to testing it really quickly. So let's say we're going to have a bunch of f's, and I'm going to quickly annotate this, an expertise list. Oh, actually, sorry, it's a definition list. So we're going to have a bunch of functions here. So let's actually try to do verbatim what I had here, right? So these things. Let's just copy the whole thing to here. And I'll get rid of this part, get rid of this part, get rid of this part, and comment it in for simplicity. Alright. So we have a function foo, so we have fun, foo with a list of arguments. We've got x, y, and z. And then we've got the body here, so this is just going to be a bop. And the last thing to be evaluated is the add, so we know that we're going to have addition of z here. And then we have another subtree, which is going to be multiplication of x and well, it was originally y, so let's make sure y is not dead. So multiply x by y. Right, great. And then, whoops, then we've got another function called bar, which has a single argument, bar x, and then the body of that is a call to this foo function that we define up here. So foo with a bunch of arguments, and this is going to be a bit tedious, but whatever. We're going to have a bunch of bops, so 3 arithmetic operations going on here. So add var x and 1, and then add var x, what was it, and 2, whoops, and then multiply x by itself. So mul var x by var x. So kind of going off the page there, but that's okay. And then as the top level driver of the program, we'll just sort of create the module C by, because I've made this a kind of generative, I know I haven't, actually, no, it's fine, I haven't made a generative, I need to do this. What we'll do is we'll just call compiler, compiler.compile defs, right? So it's expecting this f's, and it'll give us back a module. So let md equal the return module. And I think there's a function called LLVM, I think there's a function called dump module, which will print it to standard out for us, but we'll soon find out. So let's go into the terminal and actually run our program. Alright, wonderful, right? It's exactly what we wanted. It is just like before, right, where we had this, and now if we compare it to what we have now, as you can see, pretty much the same, albeit the names that we had before don't really matter, because as I've said before, the names that LLVM has here are they're generated by a slot tracking mechanism, and the reason for that, rather technically, is that when you see this free here, and it's referring to this instruction, and the actual real C++ LLVM representation of this, it actually is storing a pointer to this defining instruction. Like there is no concept of names, really, like they're actually generated on the fly. And if you want to test this, you can actually just sort of rename this to something like 5, and you'll see that LLVM will complain. But now, to kind of make this a bit more useful, we'll actually compile it into something. So we'll use LLC to compile this. So LLC of we haven't emitted it to anything, so let's emit it to a file called out. I don't know if that's done that for me, has it? No, it hasn't. So let's actually do this instead. Front end line LLVM dot string of LL module of the module, and I'm hoping this does something a bit differently, but perhaps not. Yeah, but it has, right? So I think it must be a different virtual file that it's printing to. So there we go. Now we've got the contents in a file that we can use LLC. We could have actually just piped it into LLC, but it doesn't matter. So we'll give it out.ll. As you can see, no complaints at all. And if we view it, we get x86 assembly just like we would expect. And just for fun, we can also invoke this with different arguments. So we can say that the machine architecture is actually, I don't know, let's go 64-bit ARM. And as you can see, haha, we've got it. Right, so that's good. So I'm not going to bother to write a C program that actually calls it. I'm just gonna you're just gonna have to trust that it actually does what we want. So yeah, that's really it for this video. In the future, I'm hoping to make a video where I actually create a parser for this this language that we've described here, because it's very straightforward, right? It's kind of like the compiler exercise 101 is to create an arithmetic parser, and then adding this kind of comma separated values and a sort of delimiter here and a name and a semicolon is a very straightforward addition to that. So yeah, but I think even if you aren't interested in LLVM, I think this is a good sort of beginner compiler project, for the simple reason that necessarily if you were to linearize out arithmetic, you're always going to get something that's straight line. Like you're always going to get something that fits into a single basic block with no branching in between. You branch into the start, then you branch out at the end via this terminating instruction here. So that has various qualities in different areas of compilers, but I don't want to ramble on too much. But in effect, there's various registry allocation algorithms that benefit very heavily from having a static single assignment form, which this will sort of necessarily linearize into, because it's already an SSA in effect, because there's no way to sort of create there's no way to rebind a value. So in a future video, I'll probably show you how to emit this without using bindings, because I think the bindings are fairly overkill here. It's very straightforward to just do the linearization yourself, then emit this as text. And that may sound a bit bizarre, but a lot of compilers actually do this. So for example, Milton, the standard ML compiler, does this, and a few others that aren't coming to mind. But it is definitely a strategy you can use, especially since on different platforms actually packaging LLVM into a library that can be loaded is quite annoying. So that's another reason why conveniently I've avoided explaining how you would install this in different systems. So on my Linux system, it's fairly straightforward to get up and running with this. So yeah, hopefully this wasn't too fast-paced and I haven't minced my words too much, but hopefully it's useful to someone out there to show you how convenient it is. Mostly because a lot of people don't get into LLVM because they assume that you need to be some sort of C++ aficionado, which is true if you're doing sort of really involved in tree work with LLVM, but the bindings are sufficient, I would say, to actually write a sort of good compiler that targets LLVM. And of course LLVM is doing all of the heavy lifting here. It really just comes down to this very short program, really. This is not even 70 lines, and it's it's even formatted with different line splits in a certain way. So this is incredibly short, and it's a really good beginner project. So I would advise people to do it, just to get started with the LLVM bindings. And I'm sure there's other languages which have very similar bindings that are very productive. But also just because, like, if you were using C++ for this, you would find that to encode things like this idiomatically is a complete waste of time. Like, you would have a sort of strange class hierarchy, or you would have someone trying to shill you on standard variant, or some sort of weird encoding, right? Whereas it's so natural in OCaml and other functional programming languages such as Haskell and others, to just encode data this way, to encode recursive types inductively, right? And then write structurally recursive things that, even if it's calling into an imperative API, which expects us to sort of, manually position a builder and then emit certain instructions of certain building, instructions, it's still incredibly productive, right? So from, in the space of a very short period of time, I hope we've basically started with nothing and got something, right? We've now got, native assembly for, ARM v8, which is not what we had before. We had nothing, right? So yeah, I think that's where I'll end the video. But if anyone has any comments, feel free to leave them below. I'll try to get back to you. And yeah, hopefully I will probably create another video, as I've said already, probably twice now, that does creates a parser for this. And the reason I haven't done it here is, again, because I think it deserves its own video, and hopefully that'll be up on my channel if I choose to make it very soon. So yeah, thanks for watching, everyone. Hope you have a good day.